Okay, for this whole chapter, we've been talking about rate laws being determined experimentally. Now, the first caveat that we gave you was that we can't use the reaction to determine what a rate law would be unless it was an elementary step. In the case of an elementary step, the rate law is equal to the concentration of the reactants raised to their stoichiometric coefficients. And so what we have here is a question about a mechanism. And in order for a mechanism to be valid, it must, one, agree with the observed rate law, and two, it must add up to the overall equation that we're looking for. When we deal with an overall equation, it doesn't necessarily represent the exact collisions of the molecules that are taking place in a step-by-step sense in order for reactants to go to products. There could be other intermediate steps in between. And that's when this idea of a reaction mechanism comes into place. The reaction mechanism consists of every elementary step-by-step reaction in order to go from products completely to reactants, including any intermediates required. So in this particular problem, it says, here's the rate law that we determined elsewhere experimentally, and we want to know if the mechanism could be correct. And so we want to offer an explanation for that. So let's see if it meets the first reaction or the first mechanism requirement, and that's that the overall kinetics of all of the elementary steps has to equal the observed rate law. Okay, great. Well, what's the overall rate law of each of the elementary steps going to equal? Well, notice that each step is labeled as either fast or slow. What we say is that the overall rate of a reaction mechanism is determined strictly based on the slowest elementary step. And so what we do is we look at the slowest elementary step and we think to ourselves, what would be the rate law for this elementary step? Remember, we can use the stoichiometry in the reaction to directly write the rate law for an elementary step, but only an elementary step. So let's take a look. We would get rate equals K times the concentration of the first reactant times the concentration of the second reactant. And they're the same reactant. So NO2 concentration times NO2 concentration just boils down to K times NO2 squared. So what do we find? It is in fact consistent with that rate law that was proposed earlier. So now the next requirement is that the reaction mechanism add up to the overall reaction being studied. And so what we do is we cancel out things that appear both on reactant and product sides of the reaction. So for example, 1 NO2 in the product side will cancel with 1 NO2 in the reactant side. 1 NO3 on the reactant side will cancel with 1 NO3 on the product side. When I'm done canceling, I just write down everything that's left. So NO2 plus CO goes to NO plus CO2. And let's take a look. Yeah, those two reactions are the same. So could this mechanism be plausible? Absolutely. It meets all the requirements. That's it for Gen Chem. That's it for this entire set of problems. Hooray.